Okay, so first I'm going to talk about POD, reduced order modeling for Navier-Stokes equations. This can be, of course, applied to other complex PDEs. Then, in the second part, I will talk about numerical methods for partial differential equations with random inputs. So, what is reduced order modeling? Well, given a function, you represent another function that requires much less data to define. The function could be explicitly defined. Of course, this is the most simplest way to define reduced order models. So suppose you have a function that is explicitly defined. Then interpolation or least squares approximation is also a reduced order model. Now, if the function is implicitly defined, say complex PDE, if you come up with a simpler PDE representation or a sparse grid approximation, that can also be a reduced order approximation. And in fact, reduced order modeling is and has been an active field in many other fields. For example, in linear algebra, single value decomposition of given matrices allows you to come up with low rank approximation and stuff. People use it to compress data if the matrix represents images, for example. In statistics, if you have a correlated rundown field and it is Gaussian, then you can use Karhunen-Lev expansion. That is low order approximation or reduced order approximation. In fluid flows, in boundary layers, it is well known you can replace Navier-Stokes equation that models the entire fluid flow by simpler combination of inviscid model near the boundary and away from the boundary. You can assume this is inviscid and use some sort of inviscid model. In the old days, people used this kind of combination of different models to model fluid flows instead of solving Navier-Stokes equation. They would use some interface to match these two solutions. Turbulence modeling in fluid flows, another place where people have used reduced order models. Reynolds average Navier-Stokes equation, that is a reduced order model. You can think of it like that, or large dissimulation models. The spatial averaging is used to come up with another representation of complex Navier-Stokes equation. In fact, as somebody pointed out yesterday, any attempt to approximate Navier-Stokes equation using numerical methods like finite element, finite difference, or finite volume are all reduced order models. You get reduced order model with respect to some parameters, but here we are not interested in those type of reduced order models. They don't really give you the reduction that you want. Okay, so what is the kind of reduced order model we are talking about? Well, given a complex system of PDEs, we want to come up with another representation that uses small degrees of freedom. Think of 100 or even 10. Can you come up with the 10-dimensional model representing? Just like in structures, they use few degrees of freedom models. Can you come up with the small degrees of freedom that represents Navier-Stokes equation? Okay, so that is the kind of reduced order modeling we are interested in that can be used in many other applications that I will mention in a minute. So, if we can come up with such a reduced order model, then we can do many reduced order model simulations at the cost of a single simulation of the full order model. Okay, of course there is an upfront cost of solving a full order high dimensional model. I will go into the details of this later. Okay, so you basically have to solve the full order model, the standard model using your favorite numerical scheme, finite volume or finite element or whatever, and then you have to store it. Okay, you can do it offline, right, using a huge storage, and then based on the stored data, you're going to reconstruct the model, Navier-Stokes equation. Okay, and that will have small degrees of freedom. So why do people do reduced order modeling? Well, approximating nonlinear complex PDEs using standard methods like finite element or finite difference are expensive with respect to CPU time and storage cost. Examples, optimal control problems. You have seen the complexity there. I will give you some more detailed examples in a minute. That requires multiple state simulation because all the algorithms are inherently iterative in nature. Okay, so you would have to do forward, backward sweeps and so on. In feedback control problem, ideally you want to do simulation in real time. Okay, and there are classical problems like continuation and homotopy methods for computing state solutions, and parametric studies. If your problem involves many parameters and you want to do parametric studies, then the simulation is very demanding, right? Okay, here are some motivating examples with more detail. Optimal control of PDEs. Here we have a cost functional that we want to minimize, for example, subject to some nonlinear PDEs, just some abstract PDE, okay, some time-dependent PDEs. Then a joint equation, as I pointed out yesterday too, it's a backward in time PDE. So it has a minus sign and it has a final condition. So, and also this is coupled to the state equation. So typically you have to solve this PDE forward in time and then get the solution. You come back and solve this backward in time. Well, if you get the solution, since you're solving numerical, you have to store it, right? In all the time instant, and then you have to integrate this backward in time with the stored information of u, and then you have to also take care of the optimality condition, update the control, and so on. So it's a pretty demanding problem, both storage and CPU time wise. So let's look at one more, or maybe a couple of more. Closed loop feedback control problems with unsteady state. Let's look at the, as I said, if you have feedback control problem, then you have feedback law, right? Like this. In the linear case, to compute this feedback law, you have to solve either using LQR or LQG, linear quadratic regulator, and that requires, this formulation, for example, requires Riccati equation solved. That is an n squared differential equation. You have n squared differential. N could be, say, even 1,000. So you have 1,000 squared. You are talking about differential equation to solve. It's a very complicated equation to solve in the linear case. Okay, it's not a trivial problem. In the nonlinear case, you are stuck with, if you want optimal feedback control, then you are stuck with this thing. You have to solve this thing, right? Hamilton-Jacobi-Bellman equation. V is the value function. Many people have talked about this thing here. The difficulty with this is, you can see the value function has a derivative with respect to u. U is the state, okay? And even if you discretize it, okay, typically you discretize, u could be a velocity. You're going to have a vector, right? That will have millions of unknowns, so thousands of unknowns. Then even if it is 1,000, you see you have 1,000th order PDE, okay? Typically you have 3 maximum spatial derivative. So this is a very complicated problem to compute. But if you can use, say, the reduced order modeling and reduce the state vector to, say, 10, then you have, or even 3, it would be ideal, right? This become a feasible problem to solve, okay? So this is my second motivation. The third one is solving stochastic PDE. This is my stochastic PDE. Many people may not agree. So this is a PDE, okay? This I have a heat equation, okay? Diffusion equation. Think of U as some temperature. K is heat conductivity in that case, and I'm assuming K is random. Okay, it's a random field. Okay, Kx is a heat conductivity is a random field. So that makes the whole problem a stochastic PDE or PDE with random input. Okay. Now, if you further assume this random field is Gaussian, then you can come up with a finite representation, approximation using, for example, Carhoon-Love expansion. Okay. And here theta I, in the case of Gaussian random field, after Carhoonan-Love expansion becomes independent random variables, and you have this assumed probability distribution. So you can use, for example, this so-called polynomial chaos expansion. I will talk about this thing towards the end of this talk. That allows you this. This is you have a expansion, finite time expansion. You assume the solution as two finite moments. Then you have this expansion. Okay, some kind of Fourier expansion. Okay, and then you take the PDE I showed you earlier and project it onto the polynomial space spanned by phi I, and you get this projected PDE. Okay, so simply a Galerican projection. And if you look at the dimension of this PDE, number of PDEs you have, that is m. Okay, and m is given by this n plus d is Cn. Okay, so d is the number of random variables that came up when I used this Carhoonan-Love expansion to expand the random field, that is, you know, the heat conductivity, right? So that d could be large. Okay, unless, you know, the covariance as correlation length that is large. Okay, so you so d could be large. Then see, n is number of terms. That's spatial discretization. Okay, so total number of equations m can grow if d is large or n is large or both. So here's another place you can use reduced order modeling. Where do you use for the spatial discretization? This can be made small by using reduced order modeling for the spatial part. For solving this PDE. Okay. Okay. So that is one example. Here is the example: stochastic optimal control problem. Same story here. You will be solving a state equation. This thing coupled with a joint equation. This is an optimality system. You have a stochastic optimal control problem. Here even complexity is even worse. You know, in the previous example I just had this. Okay. So imagine now you have a control, and then you want to minimize the post function subject to this state equation. Then complexity is increases. So this is another place reduced order modeling can help. Okay, approximating the state equation. Okay, so what is reduced order modeling? I haven't defined this yet. I'm going to go in several stages. Okay, so this consists of first choosing a reduced order basis to span your solution or to approximate the solution space. Okay, so that is a critical step in this construction. Okay, and this process requires several offline simulation of the high dimensional discrete system. Once, upfront thing. Okay, then you seek the solution. This is basically a Galerican projection idea. You seek the solution as a linear combination of the basis, and then you compute the coefficients in the expansion by solving the PDE through Galerican projection. Okay, and here the computational cost would be small if the dimension of the basis is small. That is, I'm talking about this dimension is small. Okay. So how does one determine this basis? That is the crucial step. So let me talk about this thing yet next. The key to effective reduced order modeling is having an effective basis. That without that you cannot reduce a dimension. For example, you have seen people use Stokes eigenfunction, right? Just for abstract construction of existence proofs and so on, right? If you use those eigenfunctions, you won't get reduction. Okay, that converges as n goes to infinity with those basis functions, eigenfunctions of Stokes operator. Okay, that is not a good choice. Okay, so here we are going to use a very rich basis. Okay, so our focus here. So I'm going to there are several methods to construct this basis, reduced order basis. This is just one of them. I'm going to talk about POD, that is proper orthogonal decomposition type reduced order basis. There is another one called reduced basis method which is a bit more general technique, but it's not as effective as this POD. So what is POD? Well, let me go slowly here. POD first requires generation of a snapshot set. Okay, I will define what this is in a minute. Then you have to remove the redundancy from the snapshot set. Okay, so you are going to rely on the snapshot set to generate or come up with a POD basis or construct a basis that has low dimension and approximates the solution space well. Okay, so key to having effective basis is to generate a good snapshot set. Without a good snapshot set, you won't get reduction because we rely on the snapshot set. That's what I said, in the beginning. We will store the data and then reconstruct. So you generate snapshot set. This simple example is storing solution at different time steps. Okay, so time snapshot is one way to do it. You can do parametric snapshots and so on. Okay, so since we are relying on the snapshot, your basis is going to be as good as the snapshot you constructed. Okay. Okay, so effective reduced order modeling depends on the basis that you construct, and you cannot update this basis adaptively always. In some cases you can, if you are doing real-time computation using this reduced order model and you have a basis and fix with your reduced order model, you cannot go in the middle and try to reconstruct the basis because you are doing real-time computation. If it is not real-time, of course you could adaptively update the basis so that your model is robust to parameter changes, so control action and so on. So it can be a costly process in the middle of an optimization. Therefore, we need to get all the information needed in the beginning before you start simulating with the reduced order model. Also, you had to minimize the computational cost of snapshot generation. Okay. Now, suppose you have a model and that involves parameters, then you have to take that into account. That is a challenge in reduced order modeling because if you fix your parameters and generate snapshot and come up with a basis, then your basis is tied to the parameter that you used, right? If you have a parametric problem that involves, say, initial condition, geometry, media coefficients, all that, that could change. You may want to use the model with a different set of parameters when you do simulation. You don't just say use the same parameters all the time, right? Your geometry may slightly change, right? Okay, so you have to take care of this when you generate snapshots and construct the basis. Okay. So how do we generate a snapshot? At this point, it is little ad hoc. Okay. So people have employed steady state solution corresponding to several design parameters. That is one way to come up with snapshots, or time dependent state solution for a fixed set of parameters evaluated at several time instance. Several state solutions corresponding to different set of parameters evaluated at several time instances. These are some of the techniques employed to generate a rich snapshot. Okay, and these snapshots, as I said, generally generated by solving PDE models by employing standard discretization techniques like finite element, finite volume, etc. And in some instances, people have used experimental data. This POD model reduction is popular among experimentalists too. So that data has also been used as snapshots. Having advanced knowledge about the states to be simulated helps. You have to incorporate if you know that, or if you are thinking of optimizing or controlling, then having some idea about the control trajectory helps in generating efficient snapshots. For time-dependent system, many approaches have been employed. including time-dependent boundary conditions, even for steady-state problems, so that you get rich transients. Some people have used impulse forcing to excite many modes in rich dynamics. Then collect the snapshots and then construct the basis. So these are some of the ideas employed. There are some systematic methods available for generating snapshots. Intelligent sampling of parameter space. That is one way to do this a little bit more systematically. Intelligent sampling in parameter space can be costly and result in bad snapshots. You can do unintelligent sampling if you want in time. That doesn't cost any storage penalty or CPU penalty because you are simulating full order model anyways. Okay. If you have unintelligent sampling in time, the POD will remove that redundancy by its nature. So, what are the lessons so far about snapshot generation? If the parameters used in ROM simulation or reduced order modeling simulation, if you are going to use your ROM for unbiased, then unbiased parameters, then snapshot generation should also use unbiased parameters. So when you generate snapshot, you should use unbiased parameters. If the parameters used in simulation are biased, then snapshot, when you generate a snapshot, you should use biased parameters. Parameter sampling for optimization and control is slightly different. Assume the path of the optimizer is approximately known. You have some rough idea. Then you had to include that in your snapshot generation. Okay. In general, the parameter space should cover your optimizer somehow. Otherwise, you won't have a robust reduced order model that will give you good control. It may not work. So, reduced order model is not a panacea. Okay, it's not finite element. Okay, so you have to make it a little bit more intelligent. So, suppose you know the bounds for the parameters. Let me talk a little bit more about the parameter based modeling. Suppose you know the bounds for the parameter, then you can use that to intelligently sample in a hypercube. Okay, you have several parameters alpha I, and then you know the bounds. Then you can come up with a hypercube, and then you sample it in that hypercube. Okay, without any additional information, you have to sample it uniformly. Okay, if there is additional information available about parameters like correlation, probability distribution, etc., then you could sample more cleverly. You can sample using non-uniform distributions. Okay, here are some methods that are employed in sampling. This Monte Carlo sampling, and then Hammersley sampling, Latin hypercube sampling. These are some of the sampling techniques used if your problem involves many parameters and you have to come with a reduced order model that is robust with respect to parameter variation. Okay. Now let me go into the reduced order modeling construction in general. So you start with a set of parameters. If there are parameters that you need to be concerned with, so let's say gamma k denote the set of parameter points chosen for generating the snapshots. Let delta t denote, let me write it on the blackboard. So you have a time interval to simulate, and it says 0 to t. Then you come up with coarse grid and a fine grid. Fine grid is for simulation, and then you have to sample it. So you select the solution, keep it. These are kind of snapshots. So you sample at coarse grid. Okay, simulation is of course using fine grid to use, but you cannot store. You don't have to store all of them, and you don't have to use all of them for reduced order modeling construction. So this small grid is size delta t. Okay. So suppose we have capital K parameters in the model, and delta t denotes a time sampling interval, and little delta is used for time discretization of the PDE, and little TL denote the corresponding sampling times. And now let S tilde denote the solution vector of the discretized PDE corresponding to the parameter K, gamma K, sampled at time TL. Then the total snapshots is equal to n, which is k time L vectors. Okay, and SI here is the snapshot. Okay, ith snapshot. Okay, so with this, I form a matrix. Okay, so I have n snapshot S sub I in Rm. I form a matrix S using these SI as columns. Okay, put them as columns, stack them as columns, and form a matrix of dimension m by n. So it's a non-square matrix that we call snapshot matrix. Okay, so S is equal to this matrix. Here the columns are snapshots, and is a non-square matrix. You can do singular value decomposition for any size matrix and shape, right? So, how many of you don't know SPD? Nobody knows SPD. Oh, you don't know SPD?
I don't remember.
Okay, I will tell you simply. For any matrix, you can come up with a factorization. These are three matrices. It's similar to diagonalization, but diagonalization limited to very square and diagonalizable matrices and so on, right? And SPD on the other hand, you can do it for any matrix. Okay. And what is U? U is orthogonal matrix. This is a diagonal. This is orthogonal. This capital T stands for transpose. So it's a decomposition of a matrix, given matrix of any size. You can come with this kind of decomposition: orthogonal, diagonal, orthogonal. Okay. So this is close to the diagonalization. Okay, that is limited to very special matrices, square matrices. Okay, and other properties. This is for any matrix. Okay, diagonalization gives you what PDP inverse, right? D is diagonal, PDP inverse. That is a lot more simpler than this, but this is more powerful because you can do it for any size matrix. Is it full rank, rank deficient, whatever it is. Okay. So you have orthogonal, diagonal, orthogonal product. Okay. So the first n. Okay, let me say this: the columns of these matrices are going to be orthogonal. Okay, so orthogonal matrix, right? Okay, and the columns vectors are called left singular vectors. Column vectors of U. Column vectors of V are called right singular vectors.
That need not be orthogonal.
What?
That need not be orthogonal.
Which one? Which one?
U.
Yeah, it has to be. SPD is orthogonal. It's orthogonal, diagonal, orthogonal. Okay. Otherwise, you don't have much use of this thing. If you can probably come up with a factorization like this without orthogonality, it's not much use. Okay. Okay. So the left singular vectors are the first n left singular vectors. Okay. If you do this, okay, S is m by n, right? M by n. So it's m by n matrix. So what is the size of this? This is a square matrix. Okay. This is m by m matrix. Okay. This is m by n matrix. V is n by n matrix. U and V are orthogonal square matrices. Okay. So the first n singular vectors, left singular vectors, that is columns of U of the snapshot matrix are the POD basis vectors. Okay. I will give you more mathematically justifiable explanation a little later. Okay. This is the simplest way to compute the POD basis vectors. Okay. You come up with the snapshot matrix and then take that matrix and do an SVD. Okay. There are routines, even MATLAB has routine to do this SVD. Okay. They will give you everything. Then collect the left singular vector. There is the first n vector, n columns in this matrix U. Okay. That is what we call POD basis vectors. Okay, they are orthogonal vectors by construction. Okay, now the singular value, this one is a diagonal matrix whose diagonals are singular values. Okay, if the singular values decay in value, then you can ignore some of the singular vectors, and therefore there is possibility of reducing or ignoring some of the vectors phi or ui, because that corresponds to singular values of small size. Okay, okay. So in that sense, this POD basis is similar to Kargun-Love analysis or Kargun-Love expansion. I'll talk about Kargun-Love expansion in detail a little later. So this is one way to do it. There is another way to construct POD. I will just spend one slide talking about this thing. This one doesn't use SVD. If you don't know SVD, only know eigenvector computation. This one is for you. So alternatively, you use the following approach: compute the mean of these snapshots. Okay, snapshots SI are vectors, basically array. Okay, you compute the mean of it. Okay, it's just simple mean, and then take this S bar, the mean, and subtract it from each one of these snapshot vectors. Okay, and form this matrix. That is what we call correlation matrix. Okay, and then this matrix, this square, and this has many properties. You compute the eigenvectors of this matrix. Okay, and define POD basis vectors using this formula. Okay, I will tell you why it is of this form in a minute. And take this thing, you can even normalize this these modes or basis functions, that you get normal basis. This matrix is symmetric and so on, so these vectors can be selected to be orthogonal. Okay, so again the POD subspace is span of this these basis functions. I forgot to put span here. Okay, so you take the basis vectors, span, that gives you subspace to work with, and once you have this basis and the subspace, you can do a Galericum projection of your Navier-Stokes or whatever your PDE, project it onto the subspace, you get the reduced order model. Okay, so let me next talk about the error analysis. First, I'm going to talk about the error in constructing the POD subspace. Okay, if you want to do error analysis, you first have to have an idea about the approximation theory, how the spaces are approximated, what is the corresponding error, and then you go to the PDE and look at the discretized PDE and continuous PDE and try to analyze it. And this approximation theory helps you finally, putting everything together and get the final error bound. Okay, that is the program we typically use in error analysis. Okay, so this is basically POD subspace approximation error. Okay, not the model error. All right. So here I'm going to view this POD construction slightly differently, so that I can get an idea of how the error is introduced. Okay, so I'm going to assume Yj denote the solution of y at different time instances Tj. Okay, so this is basically snapshot in time. Okay, so in the error analysis, I'm going to assume my snapshots are for a fixed parameter and selected at time instances. Okay, so basically time snapshot is Yj. Okay, now if you span this, if you form a span using these snapshots, you get a curly V space, right, whose dimension may be less than n. I'm using n of these. Okay, if you span it, the dimension of this space may be less. So let's say it's D. Okay, now for a given R, I'm going to consider the following minimization problem. Okay, let's look at this coast. See, Yj is the snapshot. Okay, this is a projection of Yj onto a space consisting of vectors psi I. Think of some basis psi I arbitrary basis. There are R of them. Then this is a projection of Yj, right? So I'm trying to minimize the error between this snapshot and this projection of that snapshot, okay, as a sum. I have n of them, okay. So I want to minimize this error, so that and come up with this psi I, so that this projection approximate this Yj, okay, with some minimum error, okay. What is this condition? This is orthogonality condition, okay. I want these basis functions to be orthogonal too, so I am putting this constraint. This is the standard delta Ij Kronecker delta, okay. Now I want to solve this minimization problem and come up with the basis, POD basis, and then I will show that the POD basis I come up with by solving this problem same as the basis I explained earlier. That is more of a computational technique, okay. So to solve this problem, you can define an operator k from V to this curly V. V is where these snapshots live. The little v is the span of this snapshot, okay. So if you define an operator from this V to curly V by this formula, okay, I picked this thing from this using this Yj psi I, okay. So if you define the operator like this, then you can show its linear, bounded, compact, self-adjoint, and non-negative operator, okay. That allows us to use well-known result in function analysis. You can find it in Reed and Simmons' book, function analysis book, that says there exists an orthonormal set psi I of eigenfunctions and non-negative eigenvalues lambda I, satisfying k of psi I equal lambda I psi I. So you basically convert this minimization problem I mentioned, this problem, by introducing this operator k. You convert this into a simple eigenvalue problem, okay, for the operator k, okay. And the theory also says the lambdas can be arranged in descending order, and all of them are positive, okay. So now see, you have an eigenvalue problem to solve to get the POD basis vectors, okay. So you solve this and get the POD basis, do a span, you get the POD subspace. And you can also, since they are all orthonormal, you can define a projection, right, using those basis vectors psi I. So this projection is something I will use when I do error analysis. Now let's look at the error. If you remember the cos function I was talking about here, okay, if I use the projection definition and replace this with the projection, okay, I get j equals this, okay. Now using the definition of projection, okay, I can further simplify this thing. It's simple algebra, okay. Some of the terms will cancel, like Yj belongs to the same space spanned by psi I, so I have another definition involving terms similar to this. So some of the terms cancel and I get this, and since these are orthonormal, this norm is simplifying to this thing, right? That is simple property because of the orthonormality. Now ki psi I, or ki, this psi I is eigenvector of k, so you have lambda I psi I, right? So if you take an inner product, k psi I with psi j, you get lambda I psi I. You get lambda I psi j. So by orthogonality, psi j is 0 unless I equals j, so you get lambda j, and you get here k psi j, right? So this formula holds. So I'm going to use that to simplify this expression further. Okay, so I have this formula. So and I can also show that is equal to this. we're using the definition of this operator A and stick this lambda in here. Okay, I swap these two summation and then stick this expression or replace this expression with the lambda I get j equals summation lambda I squared. Okay, so the error is basically sum of lambda I. So you have a control over the error. Okay, now this is basically, if you look at the definition of j is equal to this. So this is my projection error. Okay, so the POD approximation error is this. Okay, so with this I can start the analysis of reduced order model. So I'm going to describe the reduced order model for Navier-Stokes equation and see how we can approximate this or analyze error. Okay, so suppose we are interested in this incompressible Navier-Stokes equation. Omega. For simplicity, let's assume boundary velocity is 0 and you have an initial condition. Okay, so let's look at this simple problem. I'm going to use finite element framework for the error analysis. So I come up with the weak form first. Okay. Let's assume f is L2 and so on. And let's take the function or test function in this divergence free subspace. Okay. All right. So initial condition is zero of x. Okay. So this is the weak form, but is v. Okay. So the finite element approximation. Let me first introduce that. Then I will define the reduced order model. Okay. So finite element approximation is this. You seek an approximation, you sub h in finite element subspace, a piecewise polynomial subspace. You can define it on a grid. Okay, so it's basically a piecewise polynomial subspace. Let's assume I also construct this finite element space so that it is divergence free. Okay, so VH is subspace of V, that is that V, such that UH satisfies the following equation. Okay, so I take this, see VH is subspace of V, so I'm going to take this weak form and restrict it to VH. Okay, so if you restrict this to VH, okay, let me make this. Okay, so this is your finite element model. Now test functions, trial functions are in VH. Test function is also in VH. Huh? is equal to FVH for all VH. Okay. So this is a simplification. It doesn't have to be in subspace of V. This problem, I don't even have to pose it in this V. I could pose it in a mixed manner with where velocity and pressure appears and so on. And here also I can make pressure to appear explicitly and go for the mixed formulation. Okay, that's also acceptable. Okay, for simplicity of explaining, I use this simple model. So, since reduced order model requires snapshots, so you have to work with this problem. You have to simulate this, okay, first. That is an approximation of this, okay, and then you construct a reduced order model, okay. So when you speak of error, you have several errors, okay, actually two errors. One is error in a solution, reduced order solution, ROM solution, model solution. That's what you are talking about earlier. What I derived is just an approximation of spaces, so approximation theory for pair spaces. So this, you are talking about this U minus UHN. What is this? This is going to be sum of, or let's see, let me call it UD. Okay. And this is going to be U minus UH. UH is the finite element solution, and plus UH minus UD. So, in other words, I can decompose this error. This is the reduced order solution, ROM solution, and this is the exact solution of the Navier-Stokes equation. Okay, so I decompose this and argue I know this thing from finite element approximation theory. I know this, so I don't have to estimate this error. Okay, this is a phi-m solution. Okay, and there are well-known results about the error between solution Navier-Stokes and finite element solution. So I don't have to estimate this thing. So I know this. So I want to know what this error is. Okay. So what is this? That is the estimate I'm going to do next. Okay. So I'm going to simply code the results that I know for finite element error, and then estimate this. I'll show you how to do this thing. Okay. So one. Yeah, snapshot error is more or less that what we're going to compute. Okay, snapshot error. Oh, okay, that is what I derived earlier. Okay, that is this thing. Okay, this is the snapshot error. See, this is snapshot, right? And I'm going to see, I'm coming up with this projection, right? So this is sort of snapshot error. I will, when I finish, you will see. Okay, I will be using this. Okay, this kind of approximation theory in finite element you have polynomial approximation theory that we quote often, use when we analyze the error in PDEs. Okay, okay. So I'm going to further discretize these models because we cannot solve this. This is just an ODE, right? This is an ODE still, right? Okay, so let me write down the reduced order model. This is sort of a semi-discrete finite element. It's not a fully discrete, right? In practice, pardon? Oh yeah, right. So so let me discretize this thing, finite element model. Let me discretize this. So let's use, to discretize this time derivative, let me, for simplicity, use a backward Euler scheme. Okay. So if I use backward Euler scheme, then I get UH n, okay, minus UH minus 1, right, over delta t, and then you have Vh plus nu gradient UHN, gradient of VHN of VH plus UH dot gradient of UH. Okay, for all VH belongs to VH. Okay, so this is Backward-Euler FEM model. Okay, that I assume I'm using to generate snapshots and so on. Okay, and then let's assume your POD subspace. So POD subspace is VD. Okay, this I constructed using the POD method. Then since I'm using divergence-free solutions and so on, therefore POD subspace will also be, POD modes will be divergence-free. Okay, so VD is going to be subspace of VH, and VH is a subspace of V. Okay, so we have this nice subspace sequence. So I will be using that a little later. Okay, so so I'm assuming I'm using backward or finite element model, and I'm defining VD to be satisfying these. Then the fully discrete POD coloration problem is this. Okay, all right. Let's see. I have a trilinear form, right? And the trilinear form is a standard trilinear form people use. Okay, and that is Q symmetric. It's very well known. Therefore, you have this result. We also have this estimate for the nonlinear terms. Okay, I'm not assuming the problem is 2D or anything. It can be 2D or 3D. Okay, and driver estimate for both 2D and 3D. Okay, this estimate follows by this kind of estimate. This is Gagliardo-Nellenberg type estimate that is valid for 3D, and you can use this Sobolev embedding. H1 is embedded in L6, and apply Holder's inequality, and you get this thing. Okay, so I will be using these estimates. Now, let me first show you how to derive stability or a priori estimates for the discrete problem. Here also we use energy arguments. So you set VD equals UD in the reduced order model. Okay, you get this thing, and then I'm going to formulate this thing. I'm going to simplify these things. This is nu times L2 gradient of UDN. Okay, this term drops out. Okay, and this is equal to this this sum. Okay, this can be proven by simple algebraic manipulation. Okay, this identity is true. Now we apply Cauchy-Schwarz here and apply Poincare. Okay, you can easily estimate this is bounded above by that, and applying Young's inequality, you get this thing. Now you take this thing and stick it in here. You get the simple. After summing from n equals 1 to n, you get this bound. Okay, from this you can get this L2 bound. All right, so this is analogous to the priori estimate in the continuous case. Okay, so that bound I need when I derive error bounds. Now let me quote some finite element error results quickly so that I can use it. For the error analysis, I'm going to assume the domain is convex polygon in R2 or convex polyhedron in R3. I'm also assuming the velocity field in H1 norm is bounded in pointwise. Okay, this is the bound that does not hold in 3D. Okay, people have talked about this thing. So I'm assuming that holds. Okay, So I'm within the time interval with the where it doesn't. So this interval is small enough, so this is bounded. Okay, that's the idea. So I'm assuming this. When you assume it, I can cover both 2D and 3D. Okay. Okay. So this is the finite element formulation I wrote down earlier. Okay. I'm also using the same backward difference. So the error results available for finite element is this. Okay. If your solution belongs to HM, okay, then you can show and if you use mth degree polynomial in your finite element piecewise polynomial space, then the error between exact solution and approximate solution is order h to m. Okay, and for the fully discrete system, you have similar estimate. This time you have one more bound with respect to delta t. Here alpha denotes the order of the scheme. For example, with backward difference or backward Euler, I mentioned there this alpha is 1 because backward Euler is first order. Okay. Also, if you apply triangle inequality, you get a bound on this. Okay. So you can use the error bound to get an a priori bound. That's another thing. I will use this also in the error analysis. Okay. Okay. So let me talk about the reduced order model error. Recall this is the POD Galerich and reduced order model. Okay, UDN is the POD solution living in VD, and I constructed VD and VH such that these two are divergence-free subspaces, and VD is a subspace of VH. Okay, now let's say the error between errors En, that is the difference between finite element solution, fully discrete, and fully discrete POD or reduced order model solution is En. Then if I subtract this problem from the finite element problem by restricting that VH to VD, then I can subtract. Okay. See, this VD is different from that, so I cannot directly subtract, but I can restrict this VD or that VH to VD, and then I have common space, subtract it, then I get this error equation. Okay. Now, I want the error bounded in some norm. Okay, I'm going to use energy arguments similar to deriving a priori estimates and so on. But the problem here is, typically you set VD to be equal to En or something, right? VD equal to En, you take V equals U and stuff, right? Here I cannot set VD equal to En. That will get you see is L2 norm of gradient of En square and stuff. If I can set VD equal to En, but I cannot because En doesn't belong to VD. Okay. So what you do is use the fact that En belongs to VH. See, E is difference between UH and UDN. Therefore, and UHN and UDN belongs to different spaces. Okay, but En belongs to VH because these two belongs to VH, the bigger space. So what I do is I use the projection I mentioned earlier. I'm going to use that projection and use the fact that goes from VH to VD. So I project this error that belongs to VH onto VD and work with the projected quantity. Okay. So let VD equal P of En. Okay. That is a projection of En that now belongs to VD. Okay. So now I can set the I put that thing into the previous formula. Okay, here if I set VD equal projection of En, okay, I get this thing. Now I'm going to start estimating the terms and convert this whole thing into some recurrence relation for the error. Okay, this is analogous to coming up with differential inequality in continuous dependence estimates or uniqueness argument. Okay, so I'm going to estimate so that at the end I have a recurrence inequality for the errors relating the current error to the previous error and so on. Then I will use a Grunwald type inequality. Here I don't have continuous, I have a discrete counterpart. Apply that and solve that recurrence inequality. Okay, it's a standard technique in error analysis, in numerical analysis. Okay, so let's use the fact that this one projection. This is a projection, right? Orthogonal projection. Okay, this is perp of this, and the orthogonality, this is orthogonal with respect to this one norm. One norm is this, the gradient, this is the one norm. Okay, L2 norm of gradient is the one norm. So these two are this is perpendicular to that, therefore the inner product is 0. Okay, therefore I can simplify this term. So I am simplifying, starting from this term. So I rewrite this using the definition of En and Pn, P of En. Okay, and here I can use the orthogonality, and I get this thing is okay. Now if you put this thing in here, that becomes this. Okay, this, here also you can use the definition of projection to simplify. Now I use the fact that okay, En is equal to this plus that. Okay, so P of En is this, and that allows me to simplify this expression further. And next I start estimating these difference between these two nonlinear terms. Okay. First I rewrite this by adding and subtracting similar terms so that I can produce E terms and so on. Then I apply the estimate I showed you for the nonlinearity. Okay, so I first apply Holder's inequality, and then apply the Gagliardo-Nirenberg inequality. Then apply Young's here. It allows me to split it like this so that I can absorb this in the left side. That is a standard kickback argument. Okay, similarly I can estimate other nonlinear terms. Okay, by Holder's and other relevant inequalities. Now this identity holds for any if you have an inner product like this. Okay, it's A minus B times A. Okay, is equal to this. You can expand it and manipulate using simple algebraic manipulation. You get this, and you saw a term like this that can be estimated by Young's inequality, or algebraic arithmetic mean inequality. Then if I employ all these estimates, I get this differential recurrence inequality. Okay, and what you see here, this is something I can bound. Okay, I will show you. Okay, now if I sum that is another technique. Instead of integrating in continuous case in the discrete ways, we sum. Okay, if I sum it, I get this relationship between error. Okay, and that is something we know already. I computed in the beginning. Okay, so this is EL. It appears in the right side too. It's similar to the inequality that you get, and then solve it using Grunwald. Okay, so the unknown is the En, right? That's what I'm interested in, the error that appears on both sides. So these are implicit inequality.
I don't know whether you pointed out that is in fact the energy estimate we showed many times in this lecture.
Yeah.
Version of it, right?
Right.
With the L2 norm.
Right.
The second one is the direct lay norm.
Yeah.
And the sum is
They represent integrals.
So it is exactly the energy estimate.
Right.
So many times.
Yeah. This is like an integral of gradient of quantities. Yes. So similar analogous methods are employed in discrete case too. Okay. Now instead of Grunwald, continuous Grunwald, we have a discrete Grunwald lemma. There are a couple of versions. This is the one we need here. This is known as implicit version, implicit discrete Grunwald lemma. That comes with a time step restriction. If you want to solve this and get the unknown A appears on both sides, then you have to make some assumption about this quantity coefficient. Then it gives you the unknown An in terms of this thing, these are known. Okay, so I'm going to apply this discrete Grunwald lemma to this one. Okay, this has unknown both sides, identify the appropriate quantities. If you assume this delta T over nu is sufficiently small, you get the bound for the error. Okay, this quantity is bounded above by that, and we know this thing because we already computed this is equal to that, right? Some of the neglected eigenvalues. Okay, that is what this is. Okay, So you put this thing in here, you get the bound. Okay. So this is the theorem. Okay. So basically, what this gives you is this error. Okay. Of course, for the time Tn. Okay. So I bounded this. This I know. If I combine these two, I get the error by triangle inequality. If you apply triangle inequality, okay. So you get this. There's you can put there. Okay. And I know this thing. I stated that result. Finite element is well known. Okay. Stick that in the right. You get the total error. Okay. So this is how you compute POD or reduced order model error. Okay. So that's all the reduced order modeling stuff I wanted to talk about. So I have about 20 minutes left. So that time I'm going to talk about numerical methods for PDEs with random inputs in more detail. I mentioned that as an example, right, where reduced order model can be helpful. And I'm going to mostly talk about correlated random inputs. Okay, I will talk about white noise and stuff towards the end, maybe 1 or 2 slides. Okay. So when I talk about random inputs, I'm going to distinguish 2 types of random inputs. Okay, of course I'm not going to talk about Levinois and stuff. Okay, so I'm going to classify random inputs into 2 types: correlated random fields with given correlation structure and uncorrelated one. I may not talk too much about it. Okay, and we also distinguish this random input into 2 types: random fields and random parameters. Especially when you do computation, this is or computational modeling, this is useful. Okay, so if you take a problem where there are random inputs, some of them are random fields and others are random parameters. Okay, so in computers, ultimately we solve a problem that involves random parameters. Okay, we cannot say random field cannot be put into a computer. Okay, so in the random field case, a discrete representation in terms of random parameters is necessary. Okay, the discrete representation is different depending on whether it is correlated or uncorrelated. Okay, now unlike in the deterministic case, if you have a PDE with random inputs, then you are not interested in one realization, right? You are typically interested in mean or covariance or variance, higher moments, and maybe more sophisticated things like probability of solution being greater than some given quantity or something, sophisticated stuff. Ideally, you are interested in the PDF of the output. Okay, so let's look at an example problem where the inputs are random. Okay, so here I have a diffusion equation, heat equation with a forcing F with prescribed boundary condition. This is steady diffusion in some interval -1, 1. Okay, this omega belongs to the capital omega, the event space. Okay, now here F is the right hand side, that is random, but also depends on X. So it's a random field. Okay, so is this heat conductivity, that is a random field. Okay, but if you look at the boundary condition, it's an interval. The spatial domain is interval. So at the end, you prescribe boundary condition. If you assume there is random, you have random parameters. So this is a problem where you have random fields and random parameters, right? So so this is one example. Let me briefly review some of the available methods. There are 3 types of methods that at least I can talk about. Statistical sampling methods, the classical methods, in the so-called indirect methods, and there are direct methods. I will talk more about the direct methods. Okay, among the statistical sampling methods, the popular one is the Monte Carlo sampling method that almost everybody knows. Its convergence rate is independent of random variables. It is embarrassingly parallel. That means it's super parallel. Okay, but its convergence is very slow. Convergence rate is equal to or proportional to 1 over square root of number of samples. As you know, in Monte Carlo, you generate realizations. Okay, you for a given you come up with a random number and then compute the problem, get a realization. You had to generate millions of realization. That is what we call samples. And the convergence depends on 1 over square root of number of samples. That means you have to generate millions and millions of samples so that you get accurate representation and you can compute the statistics. You can improve upon this convergence by using quasi-Monte Carlo methods or Latin hypercube sampling methods. They accelerate the convergence, but they place additional restrictions and so on. Okay. Then there are indirect methods. For example, moment equation approach. This derive equation for moments of solutions, means and variance and so on, higher moments. The problem with this approach is there is a closure problem. Okay, you can't close that. You keep on producing equation that involves more unknowns. Okay, so you keep on deriving more equations for the moments. That problem is there. Okay, and it also not applicable to nonlinear problems. So if your random field is non-Gaussian. Okay, then there is a Fokker-Planck equation. This directly works with the PDF or the PDEs. You derive a bunch of equations for the PDF, but it has this boundary condition problem, and in higher dimension, this has problems similar to this Hamilton-Jacobi-Bellman equation. Okay. Okay. Then there are direct methods. I'm going to talk about some of them. There are many other direct methods. Perturbation method is one of them. Here you assume the random part is small. Okay, so the standard deviation, for example, you assume that small in your random field, so it makes a special assumption. Then you expand the solution as a power series and then compute the coefficients of that power series and so on. Okay, so this one also has limitations, and there are operator-based methods. This uses this Neumann series, assuming inverse of the stochastic operator exists and so on. Then they expand it using Neumann series. This is also restricted to small uncertainties and stationary problems, static problems. Then there is a popular method that I'm going to talk about. That is called stochastic polynomial approximations. Okay, popularized by Ganem, and then later on, lots of people started working on. This one involves global polynomial subspace approximation. So you use approximation involving global polynomials. So polynomial chaos is one of them. Carhoon and Love expansion can be used to help in this construction. That is used mostly for inputs. Okay, polynomial chaos can be used to come up with the approximation for the solution unknowns. Okay, stochastic collocation. This is taking a lot of attention these days. That reduces the computational cost quite a bit. Okay, you sort of collocate on the random space. Okay, and the issues here are finding proper polynomial subspace. Curse of dimensionality is an issue if you have many random variables, and low regularity of stochastic solution can be an issue too. Typically in stochastic PDEs, you don't have enough regularity, so analyzing this is a problem. So let's look at the formulation of the stochastic problem. First thing you have to do is to approximate this random inputs and come up with a finite representation. Okay, so you have to find an accurate representation of the random inputs first. Okay, because we are working with random fields. Okay, so we have to convert the infinite dimensional probability space, that is another thing, into finite dimensional one. So we had to do parameterization of the probability space by finite number of random variables. So the finiteness is important because we are thinking of computing, right, in the computer. So we have to come with a finite number of random variable representation of all the inputs, random parameter and random fields. For computational purposes, the set of random variables has to also be independent. Okay, that is another thing. Then develop an approximation method using polynomial methods. I will describe it a bit more in a minute. Polynomial methods or sampling methods, like collocation is one of the sampling methods. Monte Carlo is of course, but this stochastic collocation is a good sampling method. Okay, and then analyze the method and justify those approximation, convergence, and so on. And so let me first talk about correlated random fields. Suppose our inputs, random inputs are correlated, meaning you have the mean and covariance. We won't avoid grid-based approximation because they increase the number of random variables as you refine the grid. So we like to use Carr-Hunan-Love expansion if possible. You cannot use Carr-Hunan-Love expansion for all the random variables. If you have a Gaussian, then things go a lot more smoothly with Carr-Hunan-Love expansion. Okay, because see, we want independent random variables. Okay, so suppose you have a covariance function given, then you can use KL for example. So let's see what KL expansion does. Let's assume for simplicity the random field is independent of time also. Then given mean and covariance of the random field, say eta, you can determine the pairs, eigenvalues and eigenfunctions, infinity many, from this eigenvalue problem. So this is a given function. We have a correlated random field, then covariance is known. So you can solve this eigenvalue problem. Of course, in practice you have to discretize too. All right, this integral that can be done. A simple integration. Then you have a simple eigenvalue problem to solve. You solve it, you get these pairs, eigenpair. Okay. And since covariance is symmetric, the eigenvalues are real and the eigenfunctions b and can be chosen to be real and orthonormal. Covariance is also positive, therefore eigenvalues are positive and can be arranged in this descending order, and we have this KL expansion. Okay, this is a given random field. Your mean is known. Okay, that these are from that eigenvalue problem. Okay, Yn is the eigenfunctions. Sorry, the Yn is given by this KL expansion. Okay, what are Yn? Yns are centered uncorrelated random fields and random variables. Okay, and one of the properties of this is, by the KL expansion theory, they inherit the probability structure of eta, or the random field. So if random field is Gaussian, then this is also Gaussian. Okay, so since there is uncorrelated by KL theory, you have uncorrelated Gaussian random variable. So that implies independence, right? Usually, uncorrelation doesn't imply independence, right? Converse is true. But if you assume your random field is Gaussian, then do Carr-Hunan-Love expansion and get this Yn, and then you have uncorrelated Gaussian random variable to work with. So these are uncorrelated Gaussian, therefore it's independent. Now for practical purpose, I'm going to truncate this expansion. Okay, this is as infinity, so I replace this with n. Okay, that will make this n. Okay, so they are independent and n of them. So that gives me computational thing going. I have finite number of independent random variables to work with. Okay, okay. To truncate the expansion, you rely on the decay of eigenvalues that appears in Carr-Hunan-Love expansion, and they decay if the covariance function is smooth and the correlation length is large, it's not near zero. Okay, so the decay rate is faster, for example, if there is a big long correlation length. So you can use those for the smoothness of the covariance and correlation length to determine how many functions or eigenfunctions to include in the expansion. So you can determine n using those information, and you have a approximation for the random field, okay, if it is correlated and Gaussian, for example. And you can prove convergence of that approximation eta n using, for example, Mercer's theorem that gives this convergence of the covariance matrix, okay. That is difference between covariance, and this sum is 0 as n goes to infinity with respect to this max. So if covariance is continuous, this eta n converges to eta because of this inequality that holds because of this result, okay. So use this on the right side. This is pretty simple to obtain, simple algebra. Use the properties of mean, okay. Use this result on the right side. You have this convergence, okay, in strong convergence to know, okay. So here are some examples of correlation people use, okay. Exponential covariance is exponential covariance, and you have a Gaussian covariance. LC is the correlation length, okay. So the number of the terms to include in the KL expansion, that is proportional to 1 over LC. The LC is the correlation length, okay. And as LC goes 0, you see, what do you get? The correlation length goes to 0. That means uncorrelated. You reach white noise case, and the number of modes or the terms including the KL expansion goes to infinity. That becomes, useless. So this is one of the reasons why we cannot use what I'm going to describe with the white noise case, okay. There are other methods we want to work with white noise, okay. All right. This is one of the issue. Well, suppose you have an elliptic PDE. I gave an example, diffusion equation, and you have a random field coefficient. Then you cannot assume this to be Gaussian because Gaussian can take negative values, right? So that becomes an issue for the well-posedness of the elliptic PDEs. I skipped that thing when I was talking about heat equation, right? That is, I said Gaussian, but I knew you won't catch it. So this is one of the remedy, a simple remedy to deal with these kind of coefficient. If you want to, this is Gaussian, okay. So you simply add and you exponentiate and then apply Gargouin law to this one, okay. Again, you get finite dimensional parameters of the random field. Similar ideas can be used for non-Gaussian, but it is a little more complicated, okay. But there are approaches available to deal with non-Gaussian random fields, and if you want to use Gargouin law expansion, you could use it, okay. But you had to do some kind of mapping, okay. Okay, so the finite dimensional assumption, finite dimensional noise assumption is important if you want to do computation, okay. So given the mean and covariance of the random field, we want to construct an approximation, okay. This involves finitely many independent random variables, okay. We have seen one way to get finitely many random variables to represent your random fields and random inputs, okay. Now let yi be the random variables with PDF rho I, okay. Now let gamma I be the image of yi. Then since we are talking about independent random variables, you have to represent well, as there is a missing here rho I n or rho I, okay, product of rho I. That is your joint probability density of y. This is the random finite number of random variables which support gamma equal product of gamma I. That gives you a hypercube representation for the random space omega. That is because you can use the independence of these n random variables to see each one of them as the axis of coordinate system, okay. So here is an example where we can carry out this program. You have a PDE as a heat equation, or just think of just some nonlinear or linear PDE is some operator, okay. D is a spatial domain. This time domain, that is your random domain. Okay, with some boundary operator, boundary condition. U is initial condition. Assume the random field process can be parameterized by a set of independent random variables. Okay. Let Z equals Z1 to Zd with a set of independent random variable characterizing random inputs. Then you can use this lemma, Dupe-Dinkin lemma, to describe the same set of random variables. So that means this lemma says you can write u of x t w as u of x t z1, z2, zd. Basically uxt is z. Okay. So the original system can be converted into this PDE. Now you see your random domain is RD. Okay. So let me take few minutes to talk about this stochastic PDE using polynomial chaos methods. So in polynomial chaos method or stochastic Gallagher method, the probability discretization is by Gallagher method using globally supported spectral basis functions. Okay, whereas the spatial discretization, that is the deterministic part, is you can use finite element local polynomials, but and so on. Okay, in stochastic sampling methods like stochastic collocation method that I said is getting a lot of traction, that falls under sampling type method. Okay, okay. So let's say u of uxy belongs to x cross z. Z is the space describing the, or z is taken to be LQ rho. This is probability density function defined by this. Okay, so typically we assume this q is 2. That's enough. Well, no, L2. Okay, rho is the probability density function. Okay. So let's look at an example. This here we have an elliptic PDE. Okay, you first write down the weak form of this or inshootable function space. This is where the this is a standard deterministic solution space. Here we have a solution space for the random part. Okay. So we are going to assume the spatial discretization done by finite element. Of course, you could use other discretizations. Let's assume phi j is the basis for finite element space. I'm going to assume gamma. This gamma is a parameter box. It's a hypercube in Rn. You can assume that. I'm assuming, it is possible to parameterize the random fields by finite number of random variables. Then, okay, let's x j is be a j-dimensional finite element subspace with basis phi j, and let zk be k-dimensional subspace with basis psi k. Then for any fixed x, so I'm fixing this spatial, the deterministic part fixed, and then you seek approximation in the form, in this form, okay, using these two basis functions. And c, j, k are the undetermined coefficients. Of course, this blue part is basically uk, the deterministic part. So you can also write this in this form if you want. So that sort of kind of gives you separation variable above Fourier series type expansion. Okay, so where uk is the deterministic part, psi k is the random part. Okay. Now, if you do a Gallagher projection, just like in standard finite element, you get an equation. Yeah, this is Gallagher projection of the random PDE. Okay. You get an equation for CJK. By solving this, you can get the coefficient CJK. And it's clear that this system is fully coupled and involves JK by JK. Oh, this is basically problem of size JK. And the problem is, because of the way we constructed, become deterministic. although it involves j times k. J is the number of deterministic unknowns, k is the number of random variables. So the advantage is it does not involve sampling of random parameters. It also doesn't require generation of realizations of the PDEs. Okay, so I think I need to stop. It is going over the time. Yeah, maybe I will stop this thing. Okay, sorry I could not finish. That's all. Okay, thank you.
I had a question. So in reduced order modeling, you motivated that maybe from thousands of equations, we could bring it down to say hundreds of equations.
Oh, yes.
And that was a motivator. So and you said that POD order was targeted towards that. So in POD modeling, how much order did we get? Is there such estimate is available?
What is the optimal one?
No. I'm asking how much order did we gain?
Gain?
Yeah.
Typical order is, say, CPU time wise, you get 60% reduction. Okay. In most of the problems, at least. The problem complexity is less, then you go up 90%.
So let's say that the dimension is originally 1000
Then
elements or something.
right.
POD, how many? So you start with
You could work with 10.
10. 1000 to 10.
1000 is enough, then you could, but sometimes
Then you can go with 10 dimensionals, right? That's the type of
possible
question
to
they
get.
ask.
Then, the standard problems that people solve in universities, because we look at modularized problems. It is possible, but if you go to industrial problems, you flow past an aircraft or something, then you would have to use a lot more, maybe 1000 POD modes, because they will be using millions of unknowns. Right. Any other questions? Okay.